For exercise 3, an investigator is interested in improving a process for bonding photoresist to copper-clad printed circuit boards. Two factors are to be evaluated: the pressure used to apply the photoresist material and the preheat temperature of the photoresist. Three different pressures and three different temperatures are to be evaluated. The number of levels need not be the same for each factor, and there is no restriction on the total number of levels. These are just our choices. Each experimental combination of variables is repeated 5 times. Note that while Excel requires equal numbers of replicates for each combination of treatments, most statistical packages allow different sample sizes to be used. In our case, we're going with equal number of replicates per treatment. The experimenter recorded the number of photoresist defects per batch of printed wiring boards, and the coded data are shown. This is another case of an embedded spreadsheet. So if you double-click and open that in Excel, you can do the analysis, or you can copy and paste it into statistical software such as BlueSky, which is what we're going to show here. We rearranged the data and saved it to a spreadsheet, which we then opened in BlueSky software. So it shows temperatures. We have low, medium, and high, pressures, high, medium, and low, and then the defect count for each combination. We want to analyze that in BlueSky. To do that, in BlueSky, you go to Analysis, Means, ANOVA 1 and 2 way, and you fill in the dialog box. We've already done that, and here's what we put in the dialog for the ANOVA. First, we want to analyze defects, so we copied that variable to the target variable. And next, we want to analyze two factors, so we copied those into that box. We're not going to check in to ignore interactions because we actually want to see it. And we want to look at Levene's test for homogeneity of variances. We want to see the diagnostic plots and the plots of comparison and the interaction plots, and BlueSky will calculate eta squared, which is the ANOVA version of R squared. So we did the analysis, and here's the results. As usual, BlueSky starts off with summarizing the variables for each of the factors. So here's the summary table for temp, and here's the summary of defects per variable pressure, different levels. And then BlueSky gives us summary statistics for temp and pressure combined, different levels of temp, different levels of pressure. Here are the statistics. And finally, BlueSky produces the ANOVA table. Now for temp, BlueSky found no significant difference. So this is a p-value. It's greater than 0.05. For pressure, BlueSky found a highly significant difference. So this value is much less than 0.05. And for the temperature-pressure interaction, again, there was no significant difference. Once again, BlueSky goes through the summary statistics for what's called the marginal means, but for a balanced design, such as most designed experiments, these descriptors are the same as the raw descriptors, which we've already looked at. Levene's test for homogeneity of variances looks at the different temperature levels, and it gives us a p-value of 0.9. It's much greater than 0.05, so we can use the assumption of normality. Likewise, homogeneity of variances by defect levels against pressure, again, we get a p-value greater than 0.05. So we have consistent variances, and our ANOVA then is valid. Now we do pairwise comparisons. And we see the contrast of temps, high versus low, high versus medium, and low versus medium. The estimates are 1.5, 1.5, 1.1. Oh, this one 1.1 to the minus 15, so it's pretty much the same. And defects by pressure using pairwise comparison. High versus low is significantly different, so high and low are not the same. And high versus medium is statistically significant, so that contrast is also significant. Low versus medium gives you a p-value of 0.179, and that's greater than 0.05. So low versus medium is not a statistically significant difference. And comparisons for temperature and constant pressures. Here are the p-values, and none of those are statistically meaningful. Pressure for constant temperature. Again, we have two-way contrast, and we have several that are statistically meaningful. We're going to probably want to look at the plots to make sense of these. Here's a first plot that shows something meaningful. It's a plot of pairwise comparisons, defects by pressure. So we have low versus medium pressure. Lower defects looks like about 2.5 lower than the mean. High to medium pressure is quite a bit higher than the mean, around 7. And high versus low, even a little more, maybe around 12. So that's a significant difference, and we'd want to use this to set our process accordingly, probably towards lower pressure. Next, we have an interaction plot. First, on the x-axis, we have high pressure, low pressure, and medium pressure. And then in each for each pressure setting, we have high temp, low temp, and medium temp. And you can see that for high levels of pressure, all three temperature levels produce more defects than otherwise. The best settings are with low pressure, and in fact, not much difference between the different temperature settings at low pressure, but the best setting is high temperature or low temperature. And I just go with my gut and say low pressure, low temperature would be the best setting for this process. Our QQ plot shows that we have a little bit of skew on the low end, followed by a little bit of skew on the high end. And in particular, observation 21 and observation 25 are outliers. They're close to 3 standard deviations from the mean as far as residuals go. So you might take a look at observation 21 or observation 21, yes, and 25. So you see observation 21, medium temperature, medium pressure, 10 defects. That's much lower than expected. And observation 25, medium temperature, medium pressure, 36 defects. That's quite a bit higher than we'd expect. We might want to look at why that might happen. Similarly, observation 5 had a lower defect rate than we'd expect in terms of standard residuals, but it's only about 2 standard deviations lower. So we may not be able to find why that's the case. But for observations 21 and 25, 3 standard deviations, we should be able to identify a assignable cause for these outliers. The residuals versus factor plots can help you check if your model meets the assumptions of linearity, homoscedasticity, and normality of the residuals. To interpret this plot, we should look for the following things. the residual should bounce back and forth across the zero line. So 0 indicates a 0 residual on average. That would suggest the process and the response and the predictor is linear. The residual should form a roughly linear band, and for high and low temperature, that is the case. We have a little bit of an uptick at medium temperature, and again, we have both of our outliers, our big outliers, at medium temperature. No one residual should stand out from the basic pattern. Obviously, we have two that do stand out from the basic pattern, and we might fit another model to this, but I'm more inclined to look for a process difference at these levels. Finally, we have the eta squared table. Eta squared is a measure of the proportion of variance associated with the main effects and interactions in an ANOVA model. The value of eta squared will range from 0 to 1, where values closer to 1 indicate a higher proportion of variance that can be explained by a given variable in the model. To interpret eta squared, use the following rules of thumb. 0.01 would be a small effect size. If eta squared is 0.06, that's a medium effect size. And for eta squared being 0.14 or higher, that indicates a large effect size. We've already examined the effects, and the eta squared value should confirm what we saw already. So, put the graphics into your reports and the tables with the highlighting the important information. Interpret it for us and upload your report to your Master Black Belt.